All right, so today we're going to do a review for exam 3. The exam will be Wednesday. You're expected to take it here during the class period on your device, unless you've made arrangements otherwise. It will be 30 to 40 multiple choice questions on the sections since exam 2, starting with the inductive reasoning sections and ending with chapter 6 with the S and the I rules. Questions about any of that? Oh, you are allowed to bring a calculator. You are allowed to bring scratch paper. You'll need them for the for some of the problems. That being said, I do believe that most people overestimate the usefulness of a calculator. It'll help a little, but the point of many questions like the one we're about to talk about is figuring out how to set it up. Questions on any of the mechanics, logistics for this week and for the exam on Wednesday? In addition to today's review, there is a student tutor-led review on tomorrow night. I've already sent you the link in an announcement. I believe it's 9 o'clock tomorrow. So if you haven't answered questions today or that you discover between today and tomorrow night, you can ask those questions then. Okay. So first question, you're about to toss 6 coins. What are the odds that they will all come up heads? I want you each to attempt these problems, work them as if this were, our exam, and then we'll discuss. So I'll give you a couple minutes to answer the question. All right, so the key formula for these sorts of problems is you need to remember what we're looking for is number of favorable cases over the total number of cases. And the formula for something with a 50-50% chance is 1 over 2 to the number of times that you are going to run that test. So it's 1 over 2 to the 6th, or 1 and 2 times 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 1 and 2. The number of favorable cases is going to be 1. Total number of cases will be 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32, times 2, which is 64, 164. Now there is a very similar looking question I might ask, which has a very different answer. I might ask you the question, this coin has come up heads 5 times. What are the odds that it will come up heads a 6th time? And the correct answer for that question is 50%, because the coin does not care how many times it has come up heads. Each flip is independent of the results of previous flips. Okay, this one. What are the odds of rolling a 7 on 2 standard 6-sided dice? Well, the total number of cases here is pretty easy to find out. 2 6-sided dice, you multiply 6 times 6, and the total number of cases is going to be 36. But the number of favorable cases is a little trickier, because there's more than one combination of 2 6-sided dice that result in a 7. There's probably several ways to do it. I think the easiest way is just to make yourself a chart. 1 through 6 on the top, 1 through 6 on the side, and you add the numbers. This kind of feels like the dice equivalent of a truth table, where you just mechanically write out all the possible values, which is why shortcuts are so helpful. So how many so this is 36, this is a chart with 36 possibilities, so 36 possible combinations. How many of those 36 possible combinations are 7? 6 are. So the proper answer is 6 over 36, or 1 in 6. So note, the rarest combinations on 2 6-sided dice are the 2 extremes, 12 and 2, because those only occur in 1 out of the 36 combinations. So the most combinations appears in the center, which is 7, which appears in 6 of the 36 combinations, and the least is only 1 up to 2 and 12. And then as you get incrementally closer, the odds go up. So there are 2 3s, there are 3 4s, there are 4 5s. And who knows what I could ask you? I could ask you what are the odds of getting an even number on 2 6-sided dice. I could ask you what are the odds of getting something divisible by 3. All sorts of fun things we could ask. And of course, if dice aren't your thing, maybe cards. Let's say you're playing with a full deck, 52 cards. You've already got 5 of those 52 in your hand, but no aces. What are the odds that the next card you will draw will be an ace? Here again, we're using the same formula. We're looking for the total number of favorable cases over the number of total cases. There are 4 aces left in the deck. So the number of favorable cases is 4. Total cases, well, we had 52. We have 5 in hand. So 47. So 4 over 47 are the odds of drawing an ace. All right, so there will be a section on the inductive mathematical reasoning. There'll be a section on translations. Translate, the statue isn't by either Cellini or Michelangelo. Okay, so the statue isn't tells us we're going to need a negation. By either, either tells us to open the parenthesis. Cellini will use a C, or we'll use the wedge. Michelangelo will use an M, and we will close the parenthesis. All right, well, that one was easy. How about a harder one? If I don't have either $2 in exact change or a bus pass, then I won't ride the bus. All right. If tells us to open a parenthesis and that we will eventually need an arrow. Don't tells us we're going to need a negation. Either tells us to open a second parenthesis. We'll need something for $2 in exact change. We'll need something for a bus pass. When you've got two letters together, you need to close the parenthesis. Then we've got whatever that last section's supposed to be. We never used a sign for if, so we use the arrow there. And then we need a negation for the won't. And then we need something for ride the bus that does not duplicate the B that we used here. Another thing that might have helped, if you take a look at the English, there are two negation words, and there are two negations in the properly translated logic for it. Several of the answers here have three negations, which at least generally will not be the proper translation. Also note, something that looks like one should never be your answer, because that is not a well-formed formula. If you have three capital letter statements, you need parentheses clarifying which two go together. Yes? Yeah. Yeah, the negation is the only one that you can do that with. Because the other ones, you need all the other operators connect to things. So they can connect two things in parentheses. So you could have this. So you can have something like this, but you can't have like just that out by itself. All right, let's do some more. I'm going to Rome or Florence, and you're going to London when COVID is over. All right, so we've got the or. We're going to need Rome or Florence. Since there's nothing else indicating what goes together, then you just put them together left to right. And you're going to London. Then you need extra parentheses. Again, anything looking like 3 can never be right. You need to group letters together in 2s. Putting them together in 3 is not well formed. All right, let's do some of these. So another kind of question on the test will be plug in the values of true and false in a large complex statement and tell us what the truth value of the statement is. All right, so here we've got, my first step is we just plug in the values. So we got true for A's and B's. We've got false for X's and Y's, and true for A. All right, so the innermost OR here is going to be true because that's true on the right of it. This arrow is going to be false because the true on the left and false on the right. This triple bar is going to be false because the sides don't match. Then the final OR will be false because it is false on both sides. Yes?
With negation, doesn't that make the 1 0?
Yeah, it makes this one a 0, but that OR will still be
Oh,
true
right.
because of that true. And you're right, I didn't mention the negation. All right, let's do the next. It's not the case of if A then B, then if B then 1. All right, so here we go again. Plug in our truths. Plug in our if true and false. All right, so the left arrow is true, the right arrow is false. Then the value of the center arrow is going to be false, which then gets negated back to true. All right, there will be some tests for validity or invalidity. You can use the truth table or truth assignment. If R, then S, therefore not R. All right, so we could use either truth assignment or truth table. Here I'll start with the truth assignment. We'll look at premise two to be true, S has to be true. We'll look at the conclusion, not R, for not R to be false, R has to be true. We then look at premise one, and premise one is true when R is true and S is true, therefore it is invalid. When R equals 1, S equals 1, or actually it's always invalid, but R equals 1, S equals 1 proves the invalidity. You can also use the truth table. We'll start with the conclusion. When R is false, not R is true. When R is true, not R is false. And therefore, values 1 and 2 cannot give us an invalid set of values. Then we look at the S. When S is false, premise 2 will be false, and therefore it cannot give us an invalid set of values. But when R is true and S is true, premise 1 will be true, because you'll have true on both sides of the arrow, and it will be invalid as R and S true demonstrate. Two ways to do the same problem. For my money, I think the truth assignment there was a little bit easier. But it depends on the problem. Some truth assignment would be very difficult if I gave you two complex premises. All right, how about this one? Sneezing in the mask is the worst thing. All right, so here, again, I'd probably start with the conclusion. Anytime R is true, the conclusion is true. You cannot give us an invalid set of values. Then I look at premise 2. When S is false, we cannot have an invalid set of values. So then all we really have to do is look at R false, S true. When we plug that in, we're going to get this triple bar is going to be false. S is going to be true. That error statement is going to be true. R is going to be false, but it's going to be negated to true. We'll have a true on the OR, and that will give us an invalid set of values when R is false and S is true. Yes?
Are you going to require us to do one of the other tests, or is it kind of
I'll let you do what you want. That being said, I will probably give you at least one that it's much easier to do on a truth table, and I'll probably give you at least one that would be much easier to do on truth assignment. So know how to do both tests. Yes? Say that again? I don't know. I don't think that'd be particularly. I think this one works pretty easily either way, or maybe equally not easily. I think the ones that you get into trouble with is that there are some that really don't work for truth assignments. So let's say instead of this problem, let's say I gave you something like this. You probably couldn't do that on truth assignments because there's only one, you're only going to get a value for S. You're going to have to do a lot of work in trying to figure out what R could or couldn't be in these other two premises. So if you see something like this, I would immediately set it up as a truth table. But truth tables tend to take, but if you can do truth assignment, that's probably quicker than a truth table. So it's good to know both. Have more than one tool in your toolbox. You don't want to be the guy that's just got a hammer and therefore everything starts to look like a nail, as they say. All right, let's do a couple more. Oh, and by the way, I mean, there'll probably be at least one that has 3 letters in it. So don't assume that we won't go higher than 2 letters. All right, so then we'll have some where we'll have T's are true, F's are false, and we don't know the value of U. All right, so this one, the answer is the value is going to be unknown. Why? Well, because when the value of U is true, the statement will be true, and when the value of U is false, the statement will be false. Therefore, we do not know the value of the statement without knowing the value of U. If U, then not false. right, so here we plug in the different values for u. The not false is true both times. And the arrow is going to be true both times. So the answer is true. All right, here's a fun one. All right, well, here's the easiest way to do this one. The easiest way to do this one is to look and realize that the final operator is an or with a true next to it, which means everything in the parentheses is going to be true. Then we have to negate it. And the answer will be false. How many got false as the correct answer? How many of you got false as the correct answer and did it the quick way, the way I did? And good for you that did the hard work too by calculating all this out, because that's absolutely correct. Just takes longer. All right, couple more for S&I rules. What can we conclude from A and B? Well, with any and, you get the truth of each individual half. So from both A and B, you get A as well as B. How about from negated A and B? What, if anything, can you conclude from negated A and B? Yes. Right, you can't get anything from this, unless you have an additional premise. So from negated A and B and A, you can get not B, but from the negated and alone, you can get nothing. All right, what can we get from if negated A, then B, and A? Again, we get nothing. From an arrow statement, you either need to match the left. So if we have a negated A, we can get at the match of the right, we can get B. Or you need the opposite of the right. If we had negated B, which is the opposite of B, we can infer the opposite of not A, which would be A. All right. Questions? How y'all doing?
I think it's mainly just the S and I rules, tripping me up.
Okay.
Is there going to be like a specific on which one to use? Like detailed instructions, like what? Can you conclude anything by using the S rule from this certain formula?
Yeah, I'm not going to tell you whether it's the S or the I rules.
Okay.
But I mean, it's easy to memorize that, there's 3 S rules, 3 I rules. If it's a regular and, you use the S rule. If it's negated or, you use the S rule. And if it's negated conditional, use the S rule. Anything else is an I rule.
Okay.
I don't know. You think I should throw some on there? Would you like that?
Probably not. I was just-
That's a great idea. Let's not have any idiomatic arguments on the test. How's that sound? All right, you all thank her later. So, good job. Any other questions? How you all feeling? A lot better than you thought? Good. Well, I mean, this is like prior to exam 1, don't get cocky. This is, in my opinion, exam 2 is easy. Exam 1, 3, and 4 are hard. So treat this like you wish you treated exam 1 and take it serious. Yes.
Are we still with the
Sure, I can talk a little bit about that. And it's good that you asked that because that only shows up all the time. And I would, if I were a betting man, and maybe I've suggested that I am in this course, I would expect it to show up on exam 3 and exam 4. So only always introduces the second term of a conditional statement. So if I say, only if I pass the exam, will I pass the course? The only if introduces the second term. So it introduces the I passed the exam, then the other clause has to be I passed the course. And often this looks very awkward and unintuitive. The other translation that people confuse with only if is just if. And just if is triple bars. But regular if introduces the left term. Yes, sir.
So, just if and only if, so just if by itself, and only if, or like three ifs.
So just if will indicate that you need a triple bar. Only if introduces, it's going to be an arrow, but the term immediately after the only if is the second term. And if it's merely an if without the only or the just, then the if usually introduces the left term. Though there are some weird English patterns that could make it do differently. Like if you put it at like the end of the sentence or use there's certain, if you use passive voice or something stupid like that. All right, on that note, enjoy your spring day. 2.5 weeks left in the semester. Time to hunker down. Thank you. Be good.